Welcome to the kitchen, intern. Grab your apron, because today, this explainer is going to show you exactly how to transform a bloated, dangerous, amateur container setup into a lean, production-ready DevOps masterpiece. We're going to treat your CI/CD pipeline exactly like a high-end restaurant kitchen. Listen, if your current Docker builds take absolutely forever, ship with a bunch of unnecessary junk, and basically leave the back door wide open to attackers, well, you are in the exact right place. We're diving deep into multi-stage builds, layer caching, automated vulnerability scanning, and secure registry pushes using GitHub Actions. By the time we wrap this up, you'll be cooking up container images that are incredibly small, blazing fast to build, securely locked down, and, actually maintainable for the long haul. So, let's get cooking.
Okay, let's just dive right into this. Look at the absolute kitchen nightmare of that naive setup. We're talking about a Docker image for a simple 200-line Python web app that clocks in at a massive 1.24 gigabytes. That's huge. It takes 4 agonizing minutes just to push it to a registry, and it's literally packed with 47 known vulnerabilities. Why does that happen? Well, it's because it contains a full development toolchain, compilers, headers, test dependencies. Your production environment absolutely never needs any of that just to serve an application. Now, compare that to the blazing fast ProChef version we're going to build today, 48.3 megabytes. That is 26 times smaller. It pushes in 12 seconds, and it only has 2 vulnerabilities, which are way easier to manage. It's the exact same app, same functionality, but built with actual professional precision.
So you might be wondering, how do we drop all that weight? We do it using multi-stage builds. Think of this exactly like separating a messy prep kitchen from a clean plating station. In step 1, the builder stage. That's our prep kitchen. We use a base image that has all the heavy tools, right? The compilers, the pip caches, all the knives and pots we need to prepare our application dependencies. But we don't serve the cooking pot to the customer, do we? So in step 2, we copy only the essentials, just the finalized installed application packages. Finally, we move to step 3, the runtime stage. This right here is the plating station. It's a completely fresh, slim base image that contains absolutely nothing from the prep kitchen except what we explicitly carried over. No compilers, no build artifacts, just a clean slate ready to be served up to production.
Now, the absolutely crucial point here is that a master chef preps ingredients in the right order. Intern, if there is one mistake I see juniors make all the time, it's this. When you write a Docker file, you're instructing Docker how to build layers, and Docker caches those layers to save you time. But if you just copy your entire app directory into the image and then run pip install, any tiny little change you make to your application code is going to bust that cache. That forces Docker to download and reinstall every single dependency from scratch. So order matters immensely. You must always copy your requirements.txt file first, then install the dependencies, and actually only after that do you copy your application code. This guarantees your heavy dependency layer stays perfectly cached unless you actually go in and change a dependency.
And honestly, this brilliantly illustrates the real-world power of that prep work. Notice the massive time drop in these cache states? By combining that correct Docker file ordering with GitHub Actions layer caching, specifically using the setup buildx action to save and restore layers between your continuous integration runs, our build time just drops off a cliff. The first run with a cold cache takes 1 minute and 43 seconds. Okay, fine. But on your next commit, where maybe you just tweaked a few lines of code and the dependencies remained exactly the same, a warm cache drops that build to an incredible 12 seconds. No network calls to fetch packages, no dependency resolution, no compiling. On almost every single pull request you make, your Docker build becomes essentially free in terms of time. It's a real game changer.
But listen, a good kitchen needs a bouncer at the pantry door to keep out the trash. When you run a Docker build, the entire directory gets sent to the Docker daemon. If you aren't careful, you're sending hundreds of megabytes of garbage before the build even starts. We solve this using a Docker ignore file, which works exactly like a Docker git ignore. You absolutely must keep heavy Git version histories, testing coverage folders, and temporary caches totally out of the build context. And most importantly, you must use it to block dangerous .env files. If an environment file containing your database passwords or API keys accidentally makes it into your image, it's baked in there forever for anyone to find. Baking secrets into an image completely ruins your pipeline's long-term security. Keep that bouncer strict, and your pipeline will stay healthy for years.
All right, before our perfectly prepped meal leaves the kitchen, the health inspector needs to take a look. In the software world, our health inspector checks for CVEs, common vulnerabilities and exposures. Basically, these are publicly known security flaws just lurking inside the base image packages you rely on. You see, every base image contains packages. Every package has a version, and versions frequently have known vulnerabilities. Left unchecked, you're actively shipping those vulnerabilities directly to your production servers with every single deployment, and we simply cannot let that happen.
Now, the easiest way to close a massive security loophole is right here. To pass our health inspection, we bake security in from day one by setting a non-root user. Inside your Docker file, you just simply create a user and group, let's say with UID 1001, and you switch to that user before running your app. Letting a container run as the root user is exactly like leaving the restaurant safe unlocked with a giant neon sign pointing right at it. If an attacker somehow compromises your application and you're running as root, they own that entire container. But if you run as UID 1001, they are trapped with zero privileges. In fact, modern Kubernetes security contexts will flat out reject your container if it tries to run as root. It's just that important.
So we know we need to check for vulnerabilities, but a manual health inspection, that just doesn't scale. We automate the whole shebang using a tool called Trivy right inside our GitHub Actions pipeline. The second our image is built, and crucially, before it gets pushed to a registry, Trivy scans it. We configure the pipeline to instantly exit and fail if any critical or high-severity CVEs try to sneak through. If it finds a vulnerability that has an available patch, the pipeline turns red, and that image goes absolutely nowhere. You can even configure it to upload a SARF file, which beautifully displays these alerts right inside your GitHub Security tab.
Assuming our image passes the scan, we need to deliver our finished meal securely to the registry. In this case, AWS ECR, or Elastic Container Registry. But how exactly does GitHub Actions prove to AWS that it's allowed to upload? Well, the old amateur way was to create an AWS access key and just paste it into GitHub secrets. That is a massive risk if those keys ever leak. Instead, we use OIDC, which stands for OpenID Connect. This allows GitHub to securely request short-lived temporary authentication tokens from AWS for the exact duration of the push. No permanently stored credentials, no hard-coded keys, and dramatically less risk for your long-term operations. It's incredibly smart.
Now, a true master chef knows how to serve any customer anywhere. Let's talk platform strategy for a second and see how this builds incredible flexibility and real cost savings. If you're deploying to the cloud, you are likely looking at ARM-based processors, like AWS Graviton instances. Those often cost about 20% less to run than standard Intel chips. But here's the catch. If your image is only built for standard AMD 64 architecture, it's going to have to run in emulation on ARM. That makes it slower and totally wipes out your cost savings. By leveraging the Docker setup QEMU action in GitHub, we can actually build for both Linux/AMD 64 and Linux/ARM 64 simultaneously. One single pipeline push generates a multi-platform manifest. So wherever that image gets pulled, whether it's a developer's Mac, an Intel server, or Graviton node, Docker automatically grabs the perfect architecture.
For the ultimate professional polish, we need to provide a receipt and an ingredient list to our customers. When we push the image to ECR, we enable two crucial flags in our GitHub action: SLSA provenance and an SBOM, which stands for Software Bill of Materials. This provides cryptographic proof of exactly what source commit built the image and a complete verifiable list of every single software package inside it. This level of supply chain attestation isn't just about passing some quick audit, it's really about making sure your container pipelines remain fully maintainable, trackable, and secure over the long term. And finally, we tag the image with an immutable commit SHA digest.
All of this preparation culminates in your tagging strategy. When you deploy to production, say using Kubernetes, you must always use the exact SHA digest, like that SHA.F3A9C12 example. That is an immutable pointer. It guarantees that the exact bytes you tested and scanned are the exact same bytes running in production. The main tag simply tells you what the latest branch build is, and the latest tag, well, that's purely for local developer convenience. You literally must leave the mutable latest tag off the production menu completely. If you tell Kubernetes to run latest, you have absolutely no guarantee of what version is actually spinning up if a node crashes and pulls a new image. Just don't do it.
Okay, take a breath and look at what we've accomplished together today. We just took a bloated, vulnerable 1.2 gigabyte mess and turned it into a hardened 48 megabyte marvel. We utilize multi-stage builds to cut all the fat. We use layer caching to drop our build times down to a crazy 12 seconds. We deployed Trivy to stop vulnerabilities in their tracks. And we used OIDC to push multi-platform images securely to ECR with full cryptographic receipts. All of that automated directly from a simple Git push. So, intern, our tour of the kitchen is officially over. The real question is, are you ready to fire up the stoves, apply these steps, and finally build your own production-grade CI pipeline? The kitchen is yours. Have fun building, and I will see you in the next explainer.